Welcome everybody to the first Friday mathematics seminar at Simon's Rock. My name is Ken Knox. I'm a faculty member in mathematics here today and every day. But today, today we're very honored to welcome Dr. Candice Price. Dr. Price is a mathematician and assistant professor at Smith College in Northampton, Massachusetts. Born and raised in California, Candice has a bachelor's degree in mathematics from California State University, Chico, and a master's degree in mathematics from San Francisco State University. She earned her doctoral degree in mathematics from the University of Iowa under the advisement of Isabel Darcy. Her area of mathematical research is in the application of mathematics to biology, primarily in DNA topology, not theory applied to the structure of DNA. She is an advocate for greater representation of women and people of color in the STEM fields, and is a founder of the Underrepresented Students in Topology and Algebra Research Symposium and the website Mathematically Gifted in Black. Today she'll be talking to us about unraveling biochemistry mysteries, not theory applied to biochemistry. So thank you so much, Dr. Price, for joining us. Please take it away.
Awesome. Thank you so much for that introduction. Just in case, I live on like a corner and sometimes there's a lot of traffic. If I'm not speaking loud enough, or if you can't hear me, just let me know and I'll put on a mic or the headphones or something like that. But thank you. That was a wonderful introduction. It's always so interesting to hear the bio happen. And then I'm like, yeah, I guess, yeah, that is me on paper. Okay. So I am hoping to talk a bit about my research, just to give some of the background information of the kinds of things that I do, and then talk a little bit about my outreach work. So I'll be changing between slide styles, because for some reason, Google Slides is not very good with math, LaTeX, but LaTeX is great with Beamer. So you'll just have to bear with me in case I have any fun technology issues, which, why not? Okay, so I will first share my screen. I have learned that you're supposed to say that out loud as you're doing it, so people don't think you're doing weird things. Uh-oh. Okay, now I have to figure out. I practiced this. Okay. I know what to do. All right. Is everyone seeing just the slideshow now? Are you seeing the side tab? Okay, awesome. All right. So, yes, today's talk, Unraveling Biochemistry Mysteries, Not Theory Applied to Biochemistry. Anytime I'm giving a talk somewhere, the first thing that I like to do is an acknowledgement. So it's important for me to do land acknowledgements, because I am very supportive of Indigenous groups, Indigenous communities. Not only do I do land acknowledgement, which is important, but also support Indigenous organizations by donating time and money. And I support Indigenous-led grassroots change campaigns, and encourage others to do so. So I would recommend, wherever you're giving a talk, look up the Indigenous nation that is present on that land and pay respect to those citizens. So I try to do that anytime I go somewhere. I use the app called nativeland.ca. It's a really great app. It gives you even a graph or a map of where you are. So it's really wonderful. Okay, so just a bit of motivation. I'm really motivated by these pictures. These are electron microscope pictures of DNA. Then that picture is sort of redrawn, and then the corresponding knot that we believe goes with these pictures of DNA. And so a big question, or a couple of big questions that come about in the work that I'm doing is how do these knots form? How do we know we have a knot? And how can we tell that these are going to be different, right? So sort of working through that area. So the big mystery, right? The biochemistry mystery or biological mystery is, what are the topological configurations of DNA protein interactions? And what does knowing them help us understand, right? What does that help us understand about biology, about biochemistry? And so the mathematical tool that we are going to use to unlock these mysteries is knot theory. So my plan today is first to give you a little background about knot theory, some of the tools and techniques we use, and then apply them to biology, DNA. And I also have a bit of interaction in this, so feel free to use the chat. Feel free to stop and ask me any questions if um, we are moving and we're not quite sure where we're going. I'm also going to try to see if I can, no, okay. Unfortunately, your pictures are on the big screen and the slides are on the small screen. I should have thought of that sooner, but so if I do this, I'm looking at you. Sorry, that's just, okay. So what is a knot? A knot is a closed, non-intersecting curve that's embedded in 3 dimensions. So we have this sort of 3-dimensional object that we can think of as rope or string, just sort of tied together in these interesting ways. I'm going to project them into 2 dimensions because it's just easier for me to work with if I'm able to draw them. But I want to respect the crossing information. So in order to do that, what we do in these pictures is we leave sort of these gaps to show a bit of a shadow. So this is showing that this strand is on top of those strands. It used to be that this was really important to explain what those sort of breaks meant, because the knot does not have these breaks. It is a solid piece, but because of advances in video games and virtual reality, we understand that this means that part's in front. It used to be a little less so. As technology grew, some of the things that we have to explain goes away as we grow and become smarter. So one big problem that's studied in knot theory is, how can we tell if 2 knots are the same? So I have these figures here, figure A, B, and C. And in fact, figures A, B, and C are actually all the same knot. They're all the same knot type. I have the ability to sort of unravel this part here to make it so that I only have 3 crossings, and thus 3 crossings here, 3 crossings there, right? So one way to do this is to physically move these objects, right? They're 3-dimensional, they're strings, they're rope. I can just physically move them. And I will say that they're the same if I'm able to physically move the strands and get from one picture of the knot to another. This is what we consider to be equivalent. Now, I'm not allowed to break the strands at all, but I can just physically move them around. So this idea of these physical moves were developed by Kurt Reidemeister. So Kurt Reidemeister developed these 3 moves and said that any combination of these moves that change the knot diagram, the picture, they still preserve the knot type. So these 3 moves are as follows. We have a twist, a poke, and a slide. So I'll show you what those look like now. So this is a twist. So what I have here is just a string or a rope that I've added a little twist to, or I can untwist it. So if I do that, I haven't really quite changed the knot type. I've just changed the kind of picture that it looks like, but I haven't changed any of the fixed properties of that knot type, just the properties of the picture. The same goes for this kind of move. This is what we call the poke. And so what's happening here is I have this piece of the knot completely on top of this piece of the knot, right? That's what this means here. And I can sort of slide that piece all the way over, and that gives me these 2 strands here. Now the knot can look like anything else all around here, but if I just have these 2 pieces somewhere, I'm allowed to just pull them apart. I like to think about some of these moves, like if you have a hair tie or a rubber band and it gets all sort of crumpled together and you're trying to like pull it apart and then you eventually get to a circle, you're doing all of these kinds of moves to get there. And this one is known as the slide. And so what happens with the slide is I have this strand completely on top of the other pieces, and I can slide it over a crossing. I can slide it over a crossing. So I've just moved it to the other side. Now, this crossing can be any kind of crossing, right? This part could actually be below, this part could be above. But as long as this whole strand is either on top or below, I'm allowed to pull it to the other side of a crossing. So these are the three moves: poke, twist, twist, poke, slide. These are three Reidemeister moves. So any combination of these moves, if I get the same, if I do these combinations of moves, I still keep the same knot type sort of preserved. So based on that, we'll say that two knots are equivalent if we can continuously deform, i.e. do these moves, right? These three-dimensional moves from one knot to another, right? This is a sequence of these moves in any sort of order. So sometimes using these moves, it is easy to see that two knots are equivalent. I should always put easy in quotes there, because really, what is easy, all right? What does easy mean? So this is what I mean. I'm going to share with you a video of going from the knot on the left-hand side to the knot on the right-hand side. Oh, I practiced this. I'm doing terrible. Okay. So I found this amazing video on YouTube. Just wonderful. YouTube, just great. Does all the great things. But I'm going to show you going from the left-hand side knot to the right-hand side. Now, this video, not only is it great, it keeps track of what Reidemeister moves are happening. Should we see that again? Yeah, pretty cool. I think there's a way to slow it down, but I never can figure it out. Okay, so first off, we're going to do a Reidemeister 2, right? The poke. Excuse me. So I'm going to take this piece and sort of push it over. That allows for me to do a Reidemeister 1 right here. So this is going to be a twist, or really an untwist. We did a Reidemeister 3 here. Let me see if I can back that up. Whoop. Okay, I won't go any further because who knows what will happen. So we had this strand here, and then we're going to pull it over. We're going to slide it over this crossing. Looks like we're going to do another Reidemeister 3. So right here, this strand is going to slide over that crossing there. And then Reidemeister 1. And then at the very end, we do this fun thing I like to call a shimmy. Just a little shimmy, right? Smooth it out. Isomorphism, all that stuff. Okay. You want to see that again, or do we think? No? Okay. Yes, we're good. All right. I can put the link in the chat if you're like, I'm done with whatever she's got going on. I just want to watch that video over and over again. Okay, we'll do. So sometimes it is quite straightforward how to do these moves to get from one knot to another, right? It's very straightforward. One picture of a knot to another. And sometimes not so much. So I want to look at an example where it is not so much straightforward.
I had a question.
Yes,
When it came to the third move, which you're calling a slide, is it always over a crossing?
Yes, always over a crossing. So that crossing could be an under crossing or an over crossing, but it's always a crossing.
Yeah.
Yeah, great question. Others while I'm trying to figure out how to do this. Okay, can you see the slides again? Okay, good. All right, I practiced, but I'm just being all fumbly here. All right, so sometimes it's straightforward, sometimes not so much. So this is the interaction part. Okay, I am going to make this smaller so I can see everything. And I'm going to ask you, which of these knots is trivial? So what I mean by that is, which of these knots is just a simple circle? Which one of these can I turn into a simple circle? Okay, and we can vote. So we'll vote left versus right. Okay, is it the left? Is it the right? Now, one thing I want to point out is these are almost the exact same picture, except for right here. Okay, right there is the only place where they're different. Everywhere else, they're exactly the same. So let's, take a moment, vote in the chat, left versus right. Left versus right. Are people voting? It's not showing up. Are we too nervous to vote? Oh, is it because, oh, Zoom is so weird. It never told me that people were voting. Okay, I'm just waiting. My poor students. Okay, so, all right. We have a lot of rights, couple lefts. This is very normal, couple lefts, some rights. Does someone want to say why they chose the knot they chose? Does anyone feel comfortable saying that? You can also write in the chat. I will read it out loud because now I can see the chat. So you can also say if you feel comfortable with that. So I think it's the left because the right one is the one you just showed in the video, okay? The one on the right seems to have more overlaps.
I picked left because the 2 votes before me were both right.
Also a very good strategy. Okay, so left versus right. Let's see. So I'm going to use knot plot. So you should be seeing knot plot screen right now. Okay. Okay, so on this screen, I have this knot. Now, this is the picture of the knot on the left. Okay, and we can tell from this crossing. This is the knot on the left. That was the knot on the right. Left, right, left, right, left, right, left, right. Okay, so many votes for right. Let's see. I know. I just want to point out, and Caitlin may tell you all this. I say this every time. This is my favorite part. My favorite part. Because that's the thing with these Reidemeister moves. It's like, when do you know you're done? You're just still doing things. Oh, I kind of got stuck here. Maybe I did the wrong sequence and I need to do more things and I can get to the end, right? It's very difficult with just the Reidemeister moves to know what you're looking at. And this knot from the beginning, we knew exactly where to start. Right here, you're like, okay, I know exactly what to do. I'm going to pull that. I'm going to switch that. I'm going to do some. Yeah. Now, unknown one, all right, the knot on the left, because I said one of them is trivial, I didn't pull a prank on you. This is the one that's going to be trivial. I'm going to show you what that looks like. This is the hard part about mute in Zoom. Because in person, everybody like, oh, wow, what? So I added the effect for the YouTube, right? Yeah, so there's no way to look at the, I mean, there's a way to look at this and know where and just start doing things, but you never really quite know when you can stop, right? Maybe you aren't stuck, maybe you could have done something else. Randomized rooms are great, especially visually, but they're pretty difficult if I wanted to do something much more complicated. Okay, so we're gonna need something a bit stronger. Okay, questions?
I guess I don't have a question, just to comment, just to support what you were saying. Like, totally. I was like, okay, so the knot's the same everywhere else, but that top part I can see will go away. So I don't know. Maybe the rest of it will somehow, like if the other one has this like entanglement up there, but the one on the right doesn't, then
Yeah.
maybe that's the reason. But it's cool that like, you know, you don't know how it could end up working out, and it's hard to keep it all in your head if you're not used to it.
Yes, totally. Perfect, right? We don't know. And if we were given this problem, we would want to work with this one because we know where to start. But that's the thing with these Reidemeister moves is you just don't know what are the right sequence to do to get to the end, right? And how do you know you couldn't have done something else? It's very fun. It's like one of the first things that you do when you learn knot theory, and then you quickly learn that you would like to do something else. Okay, so the something else that comes up is known as an invariant. Okay, so an invariant is this property of the knot that doesn't change when I change the knot picture, right? It is a property of the knot type that won't change under the deformations. All right, so no matter what I do, pull strands, do this, that value will stay the same. So this is one way we can tell if two knots are different, if this value is different, right? It's not a great way to tell if two knots are the same, but it is a great way to tell if two knots are different. So let's talk about some of the invariants here. Okay. So this first one is what's known as a minimum crossing number. So a minimum crossing number is just defined as the number of crossings over the minimum diagram. So I've done all my Reidemeister moves and I can't do maybe anymore, and I count how many crossings I have. And I do that over all kinds of diagrams, and then I see what's the smallest number, right? What's the smallest number for that knot type? So the smallest number of crossings, or the minimum crossing number for the unknot or the trivial knot, is 0. No crossings. The smallest number, or the minimum crossing number for the trefoil, is 3. So this is a knot called the trefoil. It has 3 crossings. This is the one we saw in the video. So you'll notice in the video, I took a 3 crossing knot to a 3 crossing knot. This is a 4 crossing knot called the figure 8. You can kind of see why they call it that. Looks like a dancer. Just kidding. It looks like an 8. We have a 5 crossing knot, the 5-1, and then the 5 crossing knot 5-2. So after the figure 8, we sort of start labeling them with numbers, and just so we know which one they are in the list. There's this strategy for how we list those. We usually start with a knot that looks like this, and then we have a knot that looks like that. So right away, we can see we're stuck. There are 2 5 crossing knots. So minimum number doesn't tell me that these 2 things are different. In fact, I've not even convinced you they're different. You could be like, you just put the same knot down twice. But we can talk about how they could be different using another invariant. Tina, I did see your hand was up. Did you want to say something?
Yeah, I was just wondering, is there like an upper bound on how many minimum crossings we can have, or do at some point they like to do this start looping around in a way?
An upper bound on the minimum. I have to think about this question. I need to think about what an upper bound of the minimum means, right? So
Like, can we have like any number of like crossings, or like can we just say like, oh, we cannot have, like, you know what I mean?
yes, I do. Okay, so I think this is what you're saying, and I will say that. Yes, so the unknot, or the trivial knot, excuse me, can have an infinite number of crossings and still have a minimum crossing number of 0. The reason for that is if you think about a rubber band, right? I could take the rubber band and just add lots of twists to it, as many as I want, right? I could do it, my family could do it, my offspring, my students, everyone, just adding twists. But still, those are all just Reidemeister 1 twists, which means my minimum is still 0. Is that okay? I hope that, thanks, yeah. One fun thing to do is to show that the 1 crossing knots and 2 crossing knots are the unknot. Okay, that's also a fun thing to do if you're just talking too much. Okay, so right away we can see minimum crossing number, not super strong, right? As soon as we get to 5, we're in a bit of trouble. 6 also has many. I think 7 has 7 or 7 crossing knots. Yeah, and I think in total we were up to, is it, am I wrong? Is it six crossing? No. I can't remember. Caitlin, you're saying? Yeah, it's fine. This is Googleable, right? It's Googleable. And I think we're up to 21 crossings. I think someone has a 21 crossing. I don't even want to know how many of those there are. I do actually, but that's not for today. Okay, so the next invariant we're going to talk about is the unknotting number. So an unknotting number means that I'm going to actually change the type of knot, right? I'm going to change it in this way where I take a piece of the knot and I change the crossing. So these are not knots that preserve the knot type, but it gives me a way of seeing how many of these changes do I need to do to get to the unknot, the trivial knot. So this is known as the unknotting number. How many crossing changes do I need to do to get to the unknot? So we can see that the trefoil, right, the 3 crossing knot, has an unknotting number of 1. I just change one of these crossings. I've chosen this one. And then notice what I can do here is a Reidemeister 3, right? Just slide this part over the crossing, and then a Reidemeister 1, just untwist. And here I am with the unknot, the trivial knot. So trefoil has an unknotting number of 1. So this is great. Unknotting number of 1. This is great. Okay, wow. I mentioned to you that I can take a circle, just the unknot, and just start adding twists, right? Twist, twist, twist. And then what I can do is once I've added twists, I can take the ends and clasp them together. So that's what's happening here. I start off with a circle, add some twists, and then clasp. Add two twists, clasp. I think 1 twist and then the clasp here. That one's a little harder to see, which is why I started here. And I can do this as much as I want. But what's the unknotting number of such a knot? Tim's got a guess. 1. I only need to change the clasp. If I change one of these crossings, I can just pull the pieces apart and then untwist. So all of these, this infinite family of knots, have the same unknotting number of 1. We thought that the crossing number was bad. Look at this. But what's great is that because these are invariants, we can combine them to distinguish knots. We can use both of them at the same time to sort of think about it. So I mentioned to you that the 5 crossing knots are different. And you said, maybe in your mind, she has not proven that to us. And I know from my classes, as I'm teaching discrete right now, you can't just say stuff without proving it. Now, this will be a hand wavy kind of proof. because I won't be actually proving things, but I'll show you how this works with the two invariants. So in this case, we know that this minimum crossing number of the trefoil is 3, and the minimum crossing number of this knot is 5. But we also know that the unknotting number is 1, and the unknotting number of this knot is 1. So while they have the same unknotting number, they have different minimum crossing numbers. So they have to be different knots. Because if they were the same knot type, both of those values would be preserved. So they must be different. This is also one great way to show that the trefoil is not the same as the unknot. So let's think about 5, these two 5s. Same crossing number, but we know that the the unknotting number here is 1. If I change one of these crossings here, I will get the trefoil. So this unknotting number has to be 2. So while they have the same minimum crossing number, they have different unknotting numbers. So we can tell that they must be different knot types. So a lot of the time, if we are sort of stuck with one invariant, we can use another to help us out, right? And so there are lots of these invariants. I've just shown you 2 very basic ones that we'll see later, why I've shown you those, but there are a lot of these. And they're not just numbers, right? We just found 2 that are numbers, but we can also have polynomials. We can also have polynomials. So there are 3 well-known polynomials: Alexander, Homefly, Jones polynomial. We can also associate to every knot a polynomial. Yes, Felicia.
So are you saying that in order for 2 knots to be considered to be different, we either have to have like the minimum crossing numbers be different, or the knotting numbers be different, or both? But
Yeah.
if they're both the same, then I guess like that could sort of be a proof for showing that 2 knots are the same.
Unfortunately, no.
Okay.
Yeah.
Okay.
So one thing is that them being the same is not enough. Both of those being the same is not enough to tell us that they're the same knot. But one of them being different is enough to tell us they're not the same knot. But they are different.
It's not like it's not an if and only if, it just it goes one way. Okay, thank you.
Yeah, very good, very good. It is not an if and only if. And in fact, they're not the only ones, right? Minimum crossing number and unknotting number, you'll see soon why I chose those, but there are lots of invariants. We have polynomial invariants. We also have invariants that attach a group structure to our knots, right? And these are newer ones called Kovanov homology and knot floor homology, or also link homology. Kovanov homology is known as. So there's lots of structure here with these knots, right? Lots of structure for how to tell 2 knots are different, right? And we'll see in a bit why that's important. Why do I need to tell if 2 knots are different? Okay. And it's funny because this slide says why, right? Why? Why are you studying knots? Okay. And I'm sure this maybe is why you came, right? You promised me biochemistry mysteries, and yet you've been talking about rope and string. Okay. Absolutely. Let's talk a little bit about rope and string. So knots are a really old story, really old. So they show up in architecture, right? I have this picture a friend of mine took in Mexico of this wall, and it has these pictures of topological figures. These are really tangles, but tangles are pieces of knots. They were used as counting tools. This is a QP, right? Where the Incas used to count things and keep track. They also show up in interesting ways in biology. Hagfish knot on themselves, especially when they're in danger. They knot on themselves. They're also really slimy, and the knot helps them be slimy. I have a video of this on YouTube of like someone pulling out a hagfish that knots on itself. And I said that they were gross, and a student was very offended because she loves hagfish. So I stopped saying that now. But, you know, pass your own judgments. Pass your own judgments. But not only do not show up in this case, they're also a really old story. So when I first was learning about DNA topology, this is the picture I was shown. This is a picture of knotted DNA. So this is one of the first pictures taken in the Cosarelli lab in Berkeley of knotted DNA. And so this lab started thinking about how do these knots come about and what does it mean? What does it mean to have knots in your DNA? So, we know a bit about DNA, just a bit, right? We know its structure. We know it's 2 long polynucleotide chains. These were, the structure was determined by results from Rosalind Franklin, right? We know quite a bit about this now, right? Double helix. But the other great piece is that besides a linear form, DNA can also take on a circular form. So plasmids look like this. I think bacterial DNA can look like this. But this is a picture of circular DNA. It's tertiary structure. So secondary structure is the double helix. Tertiary is this double helix sort of wound and turned into a circle. But not only can it look like this, but as we have seen, it can look like a knot. So one big question for distinguishing these knots or telling if they're different is, if I saw these pictures, how do I know I'm not just getting the same knot out every time? So I need to be able to tell them apart. So let's talk about what knots in our DNA mean biologically. So one of the first things we're going to talk about these 2 types of proteins. So one protein is a protein that cuts a strand of DNA and it allows for another strand to pass through. So I take the double helix and I just sort of break one of the pieces and then push a piece through. It's kind of a small picture. How's that? Better? Okay. So what's happening here is we cut, it's a nick, we put the scissors in, biology. There's some scissors in your body. Cut, pass this piece through and reseal. Okay, so that's kind of what's happening. We'll talk about why our body does this. The next kind of protein, so this is called a type 1 topoisomerase or a type 1 topo. We also have a type 2 topo, and a type 2 topo takes a whole strand of DNA, cuts it, and pushes another strand through. So this, these are both making crossing changes, but at different parts, right? This is making a crossing change at the tertiary structure, and the type 1 is making a crossing change at the secondary structure. Okay, so those are the topoisomerase. Let's zoom back out. So why are these important? Why do we have in our bodies these proteins? So they're very important when it comes to replication, transcription, unknotting, unlinking, supercoiling, and they can be targets of anti-cancer drugs and antibiotics. So let's think about why we would need the type 1 topoisomerase. So if we think about the secondary structure of DNA and we want to replicate or transcribe, what we have to do is take the DNA and pull it apart. But the DNA is either circular or it's fixed at the ends. So what happens when you pull apart something that's twisted and fixed at the ends? The ends start to get all of that pressure, all of that stress of you trying to pull the pieces apart, right? And so in order to relieve that stress, we have to make a crossing change, right? We have to change so that we get more space in order to pull and reach the DNA. All right, so if we were in person, I would have these electric cords wrapped up and I would have you like holding the ends and I'd be pulling and I would ask you what's happening. And that's kind of what's happening, right? You're just trying to pull them apart and the ends are getting really stressed. And so what I need to do is a crossing change at the ends in order to release that stress so that The rest of it can be transcribed or replicated. So another thing that can happen is we can have knots and we can have links in our DNA. So what happens if we have that? Let me up. I just wanted to bring you back to this because that was so fun, wasn't it? All right. Uh-oh. Oh, I hate when this happens. Oh, wait, I know what to do. Maybe. Ooh, maybe this will be okay. Pay no attention to these extra pieces. That's not going to do anything at this point. All right, so let's say we have a circular piece of DNA. What happens when we replicate DNA? What's the end result? Why do we do that? In the chat. Maybe people are saying things in the chat. No. Wow and whoa are the last things I saw. So, Bill, you're writing up 2 circles. Why?
I'm assuming you somehow have to get a copy of the circular DNA.
Perfect. A copy. Replication happens so we can get a copy. All right, so what a time to have a tickle in your throat, huh? Oh, I know what I'm doing wrong. I made a copy of this DNA. Why do I need a copy? Why do we make copies of our DNA? Very good, Iris. Each cell has a copy when they divide. I'm just going to show exactly how this works biologically with this wonderful picture I have here. Oh my, okay. I didn't think it was going to do that. I definitely should have redone this. Okay, so what happened was that one of the pieces floated away and the other piece is still there. Huh. Wow, that was intense. It has never done that before. Okay, so they were easily separable, right? I could easily pull the blue into one cell and the orange into another cell. Apparently the orange in the other cell, I think, is in California, because where did that go? I don't even know. So let's think about, though, what happens if I have a knot. We're going to do the same thing. As Bill said, we're going to make a copy. I'm really nervous about what's going to happen next because I was very surprised last time. What do you think is going to happen when I try to put these into 2 cells? Besides the explosion part, though. I'm just gonna hit the button and see what happens. Oh no! I knew it was gonna do that. Okay, hold on 1 second. Not plot, you vixen. Now I know. Now I know I can't do that. Ugh. Should have given you a topic. Is cereal soup? Talk amongst yourselves. All right, let's try that again. Okay. I'm gonna make this a little thinner. Even though I love it, okay. Just so it's easier to see, I'm gonna double. This should not explode on us. This is what I'm used to. Okay. And then I'm going to let it go. And what is happening? I paused it, right? Because I don't know what was going to happen. What's happening between the orange and the blue?
They can't separate.
They can't separate, right? So this is a problem in a cell, right? I need it to separate. I need these two things to be able to separate from each other. So if they can't separate, then I need a protein to come in and change the topology, right? Make a crossing change so they can separate. Either at this stage, right, I can unlink them from each other, right? Just making a few crossing changes, like this blue needs to go. And I think, in fact, this program may do it for us. Hold on. Whoa. Okay, just kidding. I've never seen it move that slow. I have broken this. All right, anyway, so I need to be able to separate those two things. I can't unless I actually break and recombine, make a crossing change. Now, that's at this stage, but what if I had done it before I even made the replication happen, right? What if I unknotted this DNA knot beforehand? And that's what the crossing changes do. So that's why it's really important to know the unknotting number for some of these DNA knots, to know what would the protein need to do in order to get us back to something we want to replicate. And I want you to notice that I said want to replicate, because I said that we target these proteins in anti-cancer drugs and in antibiotics, with anti-cancer drugs and with antibiotics. Now, one thing is that we can target bacterial DNA because it reads different from ours. So we can say to a topoisomerase, we can say, don't work here. Don't change this, right? This is a bad piece of DNA. We want it to replicate and be stuck together and not be able to move into other cells and not grow, and body will take care of it because it will send a signal that says this is bad. But one problem is we'd like that to be the same case for cancer cells as well. But cancer cells are DNA that is our DNA. So effectively, we're saying to the topoisomerase, don't work on our DNA. One reason why people get really sick in some of these medicines, because the good cells and the bad cells are all being affected by this, and we can never really tell the difference. A lot of people are working on this problem, right? Trying to understand how the protein works and where it works, but it's still a work in progress, if you will. There are often questions, but if there are none, can
I had a question of, so you were saying that it normally would make a, I guess like a cut before replicating.
it can.
But would you have to make the same amount of cuts if you decide to cut it after replication?
You know, that's a great question. It depends on how linked it is. So that's a question of an unlinking number, right? And so that's something that you could sort of think about, or we could think about, right? If we took a trefoil and copied it, how many crossing changes would I need to do for those two pieces to separate? But I feel like it's not the same number, but that is me saying that from the pictures. And as we all know, just looking at the pictures is not enough.
Okay, because I was wondering if what your body ends up doing has more of like an efficiency reasoning to it.
Yeah, so that's a very interesting thing. So our bodies are actually quite efficient at this, meaning high probability of it taking care of the knot with the least number of crossing changes. So when I showed you those knots that have all those twists and then a clasp, the topoisomerase probability of hitting the clasp is highest than anything. Even though you have all those crossings, it is smart and knows where to go, to just have to work once. Now, I don't know how it does that. I think people are studying that. That's not something I'm studying. It's something I just tell people, and then I walk away in awe, and they're like in awe of me for knowing so much. But when people are looking at the statistics, when they're running these experiments, that's what they see. And so we want to know what is happening. How is the DNA shaped, the topology of the DNA, the geometry of the DNA, such that the topoisomerase knows what to do. It's just fascinating. And I will just say, when I first learned that, I was like, I am all in. Tell me more about this, because that is fascinating how our bodies are just doing this. I know we're short-ish on time, but I do want to show you, how do you even get these knots, right? Because if I didn't start with knots to begin with, why am I now worried about them? If I can get back to that screen. So there's a third protein. There's always a third protein coming into play. So this third protein is called a site-specific recombinase. Now, what this protein does is it recognizes specific sequences in our DNA. It breaks those sequences and recombines them. So what happens here is very different from what happens with the topoisomerase. If I do just a crossing change, I have not changed the sequence of DNA, just the topology. But here, I started with a red to red and a black to black. And in the end, I got red to black, red to black. So these proteins give us genetic differences in our sequence. This is one reason why you don't look exactly like your siblings or your cousins, right? One of you is more attractive. You can just decide who that is, okay? But this is one of the reasons. Our DNA code is going to be different. So how does this give us knots? Well, let's say that I have what I call a substrate. So this is the original piece of DNA. It's circular, it's wonderful, it's doing all the things we want it to do, but it has these really interesting sites to this enzyme. The enzyme would like to change these sites. So the sites, because they're site specific, what it's going to do is it needs to bring those sites closer to each other. So it winds around the DNA and brings these sites closer. That's how it does it. But once it brings them closer and changes this topology, it traps those crossings, giving us now a knot or a link. So you need both of these proteins acting, right? You need genetic differences, you need your DNA to be changing, so you need the site-specific recombinase to be working. But then if you want to replicate this DNA, you can't have it be knotted or linked, so you need the topoisomerase to come into play, and it's just going back and forth, right? All throughout your body, all the time, just doing this very efficiently and wonderfully, right? So understanding the mechanisms that these proteins are working is a big foundation of DNA topology. So a couple more slides. I'm just going to show you other things we can do with this. We can study proteins that just bind to DNA that don't actually change the topology. Sometimes viruses will have this, right? You have a bacteriophage or some protein that holds on to DNA and then tells the virus it's time to come in. And then it opens and then inserts the virus, but it doesn't change the topology. So we'd like to know, what's the signal? What does it look like inside of here? You can use other proteins to trap by changing crossings on the outside. So that's some work that folks are doing. The cartoon of that looks a bit like this. I have this protein that's holding on. I don't know what it looks like inside. I have these strands outside. If I change the outside strands, I can trap some of the things inside. You may notice, though, that I've only done with these two. I have to do with all the combinations. So it creates these really fun pictures, and then it's a mystery that you can unlock with knot theory.
I have a question. So when we're trapping these things, so is the point that we're doing that to like the DNA of like bacteria or something in order to make it so that like it can't undo it or something with whatever it's doing?
Yeah, good. Excuse me. Like I said, what a time for the throat tickle. Yes, so inside of here are some sort of crossings. But if I were to release, I wouldn't know what that looked like. So the experiment here is to trap the crossings in here so they don't get released, they don't just unravel. So in order to do that, I do have to change this part here. And because I kind of understand how to do those changes with the site-specific recombinase or the topoisomerase, I can at least know what happens here to help me figure out what it looks like in here. But yes, once I wash off this protein, I've lost all information. Yeah. The other two pieces I wanted to show you are there are knotted proteins. They're a little different from knotted DNA because they don't have these bounds. They're not closed, but they're so rigid that you can't pull them apart. So lots of people are studying how do these come about, knotted proteins. It's really cool. And some people are working with knotted molecules. These are created in a lab. I don't think that we've seen any knotted molecules in nature. But one really interesting thing is that the shape of a molecule impacts its action. And so one question is, what does a knotted shape do to the molecule, right? How does it work? What does it do? How is it changing the action? That's what I have for this. I know we are at time. So, check out my website. I have a lot of stuff about what I've done as far as outreach work. USTARS is a great conference. Mathematically Gifted in Black. Please check that out. Happy to talk with anyone about what I've done. Email, reach out. So thank you so much for listening. I'm sorry my voice is like...
Thank you so much. So virtual round of applause for wonderful talk. Thank you. So I mean, I think we've blocked off an extra half an hour on the schedule. I don't know if you wanted to continue to speak or host a conversation, but
sure,
certainly.
Yeah, that's right. I'm sorry. I remember that. Sorry, I was looking at the email today and it said 4 to 5, and I was like, oh, okay, I can do this.
Sorry about that.
No.
Maybe that was me doing that. I apologize.
You're totally fine. Yeah, I was like, yeah, I got this 4 to 5. I can fit all of that in there. I cannot. Yeah. So, right. It was mentioned my background. I did create some slides. Let me. Sorry, I'm laughing at the first one. You will too, maybe. Let's see if I can pull this down so I can see you and the slides. Wonderful. Or not. This, oh, okay. Okay, so I like to talk about my academic biography or my journey because I don't know if it's what people think happens when you become a PhD in mathematics or a professor, but I first found out that I really liked math in the 3rd grade because we did multiplication and I knew how to count and add, and I was like, I am the best at all of this. And then I learned multiplication. I was like, this is so cool how this just works. But how I learned it was with my teacher played Schoolhouse Rock. So they had these songs, and my family is very musical and we love singing all the time. And I was like, you can do music and math. Now, to be fair, this is not really music and math. It is talking about math through music, but I'm in the 3rd grade. So I think this is the coolest thing I've ever seen. I still really love all those songs, and I play them for my niece sometimes. She's over it, but that's fine. At some point, she'll enjoy it. But because I really liked math, when I was in the 4th grade, my mom reached out to my teacher because she was like, excuse me. I just need 1 second. I don't even know what it is. I'm just so excited to be here. excuse me, she noticed that I was bored in class. Oh, it sounds like I'm getting emotional, and I'm not, I promise. It's just my voice. I was bored in my 4th grade class. So she talked to my instructor and was like, I don't think this is good. I think you probably should test Candice because I think she's bored and I don't want her to be bored because she'll get into trouble. It's like she knew me. I don't know. So they tested me and they said, okay, we think you can skip a grade, especially because of your math skills. Like you really have this math mind at the time is what they said. So I got to skip a grade. I went to high school. Yeah, we're just going to skip middle school because wouldn't we all like to skip middle school? I went to high school and I went to a humanities program. So that's where I really learned a lot about connecting humanities with science, connecting humanities with mathematics, thinking about the humanities, religious studies, things like that. But I pulled a bit away from mathematics because I struggled. I struggled quite a bit in high school. And so I thought, well, you know, it wore off. The skills I had as a child wore off. I'm just not ready for this. I gotta, you know, find another route. I went to undergrad at Chico State, and I was going to major in psychology because I had just done humanities and I liked talking to people about things and helping them out. And so because I was majoring in psychology, my pre-calculus instructor reached out to me and said, you know, you're pretty good at mathematics. You should think about majoring in math. And I thought she was joking because I didn't look like a math major. I think I have a picture of what I thought was a mathematician. Hold, please. Albert Einstein. This is what I pictured. I pictured Albert Einstein. And I was like, oh, you have to be like a super genius to do mathematics. And you kind of have to look like Albert Einstein. This is all I knew. And she was like, well, you should do this. And then you can go to grad school in psychology because you have a degree in mathematics. And anyone will take you if you have a degree in mathematics. I'm at this point in my life where I'm still not sure that's true, but I believed it because I didn't know any better. So I majored in math and I decided to keep going. I did this LSAMP program, the Lewis Stokes Alliance for Minority Participation. That allowed me to get my master's at San Francisco State. While I was there, I worked with Marielle Vasquez on DNA topology. She talked to me about Isabel Darcy, who was at the University of Iowa. Now, at this point, I had never left California. And people are like, you should go to Iowa. And I said, I don't even know where that is because I didn't. Well, here's a little hint. In California, we know about California. We know about Texas, Florida, and we know about New York. Could we point it out on the map? No. It's all of that is what we would say. So there's no way I was going to Iowa. But I talked to a graduate counselor there and he was so kind and he reached out to me and he said, you'd be great here. What do you need? What can I do? And I was like, I think I'm going to go to Iowa. I did. I had a great time. While I was there, I started lots of programs, which I'll talk about. Graduated from Iowa, started at the United States Military Academy. That's where this picture is from. If I were ever going to run for office, this is the picture I would use. The one on the left I'm talking about. That's the one I would use. After I finished at the United States Military Academy, it was a 3-year position. I started at Sam Houston State University. That's in Texas. I was there for a year. I went back to California, University of San Diego. And then I started at Smith College in the fall of 2019. So you can imagine what a great first year I had at a new institution. But besides that, this year I found out that I was awarded tenure. So I will be tenured associate professor starting July 1. So I'm excited about that. I think, you know, I'm really grateful. Yeah, it's a big step. So super happy. What's happening? I'm falling apart. Okay, so during my time at Iowa, I thought a lot about my outreach. And so I came up with this service mission, which I'm going to give you an opportunity to read while I drink some water. God. I'm going to make it through. So I was being asked to do a lot of things, and I wasn't sure how to say no. And so I talked to friends, or how to say yes, even. And I talked to some friends, and they said, we need a service mission statement. And then if you're asked to do something that doesn't fit your service mission statement, you don't do it. And I thought, oh, all right, let's do this. Now you'll see, this is a very broad service mission statement. I still say yes to a lot of things, but I at least think about it first, right? I think about how does it impact my service mission? And is it doing what I say I want to do? One of the things that I did as I went to this really great conference that was run by graduate students in Binghamton, and it was called BugCat. So the Binghamton University Conference for Graduates in Algebra and Topology. It was like 10 years ago. And I loved it. And I came back to Iowa and I said, hey, we could do this. We could run a conference. So I called, I think I sent a text to 4 of my friends. The first 2 of them said, no, absolutely not. No. And then the fourth person was like, yeah, let's do it. So we all decided to do it. We put together this great conference. We wrote an NSF proposal. We got funding. And it's called the Underrepresented Students in Topology and Algebra Research Symposium, USTARS. So it runs every April. Last year would have been our 10th year. Right? We started this as graduate students. Unfortunately, we were not able to meet in person last year. So we are virtual this April. ICERM is hosting us, which is really great. It's the first time we've been hosted by a institute. And I think because of the pandemic, we were able to. Otherwise, the institutes are usually too small to host the conference. And especially what we do, we have breakout sessions for graduate students to give talks. We have poster sessions, panels, things like that. It's really a awesome conference that I love. And they're still taking applications if you're interested to just go. It's virtual. We have funding for food. So we'll pay for a per diem for the days that you're there. And we also have money for childcare. So that's how we converted our grants to pay for the conference. Instead of travel, childcare and food and collaboration grants. Other things that I have been involved in include BEAM, the Bridge for Entering Advanced Mathematics. This is a great program for younger kids, middle school, elementary school, a little bit of high school. The EDGE program, which is a program for women entering their PhD. Infinite Possibilities Conference is a conference, or was a conference that was mainly for women of color in mathematics to come together and present their research and talk about networking skills and CVs and just joining the professoriate or joining the academy or joining industry and thinking about what that's like. But other things that I've sort of started or I've been a part of, the Network for Minorities in Mathematical Sciences. This is a group on Facebook that we created, just a space where we share job advertisements, different conferences, this is going on, what's a good book for this, I've heard about this, can I do that? Just a space to network and share. I do this kind of research. Does anyone want to work with me? Stuff like that. And then MSRI Up is a summer program for undergraduates in REU, and it's at MSRI. And I am a co-director of this program. So this is my first year as a co-director, but I was a grad student mentor and a postdoc mentor. So really great programs enhancing and broadening participation, right? Because if it's not, oh, I can't be a part of it, right? As my mission statement says, got to do all these things. And so many things do, so it's great. You know, these are important to me because, as I mentioned, I used to think that you had to look like Albert Einstein to be a mathematician. And I thought about why that was. And I think it's because this is really the only picture of a mathematician I had in my head. And it's fun because he's not even a mathematician. He's a theoretical physicist. And you know, and some people would say that's the same thing. And that's fine, right? That you could say, I will not argue with you. I don't think it's the same. Some people they'd fight you in the street. that's not me. I won't. Okay. So I thought a little bit about this, and there rarely are very many images of mathematicians in the media that look like me, right? And in fact, many of them look like Einstein. There were two, though, as I was growing up, that I think sort of helped with this. So Jaime Escalante, there was a film about him, Stand and Deliver, and he was a calculus instructor or a calculus teacher in South Central LA, supporting Latinx and African American students taking calculus and passing calculus exams, and just great. Erica Camacho, who is a very well-known math biologist, is a student of Jaime Escalante. So she came out of that program with him. And then Dwayne Wayne is this amazing character from the show A Different World, which was a spin-off of The Cosby Show about HBCU called Hillman College. And he was a math major and taught classes as a grad student, I think, and fantastic. And there's this one episode where he's talking about how hard calculus is, and it's so funny because I was a kid and I was like, calculus sounds so hard. And now I teach it and I say the same thing. I'm like, this is tough. I'm just kidding. I don't. But it's just like it brings back so many memories to think about like what I thought about math as a kid. So there wasn't really a lot of media for me to rely on to see myself. And I thought about that a bit. And it wasn't actually until Hidden Figures came out that I saw Black women doing mathematics. And this had a huge impact on me for various reasons. One, I finally saw myself in the media doing mathematics, but also I didn't know these stories. And I know that's a shocker, right? Because the title is Hidden Figures. How could you not have known these stories, right? But I didn't. And I was very upset about that because I was like, this would have been huge for me at going through all of this to know this story. So I thought a bit about the impact of that on myself, and I thought about the impact of the stories that are current that people don't know and how to change that. And so I got a little boost from this great website called Lathisms. So Lathisms was this website that celebrated Latinx and Hispanic mathematicians during the month of September 15th to October 15th. And what they did is they featured every day a mathematician and their story. And I got together with three of my friends and I said, let's do this. Let's do this for Black mathematicians. Let's tell our stories. And so we created Mathematically Gifted in Black off of that. So myself, Shelby Wilson, Reagan Higgins, and Erica Graham, together we created this website. So this was our 5th year of it. It's funny because we did the first year and we're like, oh, this is great. Oh, I guess we have to keep doing this. That always keeps happening. That was like that with UStars. I was like, let's just do this one conference. And then we got an email that was like, when is UStars next year? Because we want to make sure not to have it during the same time. And I was like, oh crap, I guess we have to do this thing because people are expecting it. That's the thing. Once you start doing good work, people expect you to keep doing that work. This is a plug for not doing good work. You heard it here first. Don't be reliable. Don't be reliable. People love a reliable person. Your phone will never stop ringing. Okay, so the 4 of us came together and we created this website. We've improved, we've added to it every year. But we first started off with just thinking, these are the folks we want to feature, right? We would like to feature diversity within diversity. We want each person to tell their own story. It's one reason why we rarely feature someone who has passed. It's because who writes the story of someone from the past? Right? And so you get to write your own story and you get to share it. And sometimes we support each other by helping someone write their story, but it's usually their own words or words of their loved ones. And so it's just this amazing, great thing that we get to do. And on top of that, we were able to create 2 posters. So there were no posters like this before. The AMS did not have any posters really that featured more than one Black mathematician. They had the John Urschel poster, but we reached out to them and said, do you think we could make a historical poster that features historical Black mathematicians? And they said, sure, go ahead and design it. I reached out to my sister-in-law, who is a graphic artist, and I said, do you think you can make these pictures into stamps? And this poster was born out of that. And then after the second year of Mathematically Gifted and Black, the AMS created a poster featuring some of the people we had featured on the website. So just making a difference in the landscape, right? Sort of changing the picture, the view of what a mathematician looks like really was our goal. But one reason for this is, this is going to be a surprise, but I'm a mathematician that's a Black woman. I know we weren't sure before, but it's true. And this identity, these two identities, impact every aspect of my life, of my job, of my research, of my teaching, of my service. My gaze, how I view the world is impacted by the fact that I'm a woman and that I'm Black. And my status in America is impacted by that as well. So my everyday life, I don't get to sort of take off these two identities. They are with me at all times. And sometimes that can be very difficult. I like to think about it as this picture here, where I'm Mario, right? And yeah, I'm gonna make it. I'm gonna make it to the end. But what's the cost? I barely made it, no money, and I have no points, right? And so some days, many days are a lot like this. So it's important for me to do this work to help others who are going through this. Maybe I can make a fire extinguisher, put some of these out, and just make it a little bit more doable for all of us. Okay, so that was kind of the piece that I had to just talk about my journey. Questions, questions. Dialogue question, thanks.
I have a question. Candice, what, as professors, I'm a professor at Bard, what kinds of things could we do to help undergraduate students who are from underrepresented groups?
So it's a great question, and I often get asked, and I should say I don't always know the answers, but I know some ideas that may help. One of the things I think helps all of our students is if we recognize some of the anti-racism we have, some of the anti-racism characteristics we have, some of the white supremacy culture characteristics that we bring into the space. It's hard, right? I mean, I think those are hard words for us to think about and say, but if anything has shown us this last year or so that there is I think a big issue of white supremacy culture in America. I think it's important to recognize it, understand it, and call its name. So Erica Graham, who also does Mathematically Gifted and Black with me, gave a really great talk at JMM this year on anti-racism in mathematics, and really hits on a lot of amazing points. And I highly recommend watching that video to at least start a conversation about that and talk to our students about what are some ways we can change our community and our culture so it is more inclusive and more welcoming. I think that is a hard problem, but we are mathematicians. We do not shy away from hard problems. When I posted that picture of the knots, no one was like, I'm out, end call, right? We were all very excited to sort of dive into that and think about it. And I think we have to have that same excitement sounds weird, but that same push when dealing with this. I think it's important to have honest conversations with each other and maybe less performativeness. There were quite a few statements that came out after the summer about Black Lives Matter, but no real structural change, and that's hard because as a Black woman, I've heard a lot of this before, and I'm always like, okay, but are you really gonna do anything? And so I think we have to start having those conversations and work on changing the structure and disseminate power in better ways. And also I think when we're having these conversations, I think they have to start with a recognition of axes of privilege, because this is not an attack. This has to be a discussion. We have to come together. And I think once we realize and understand where we all are in the picture and the places where we have privilege and how we can use our privilege in those axes to support each other, I think that's really when we can do it. But I think we have to come without defensiveness and with reflection. So, yeah. And that may not answer, I was just speaking off the top, but I think that's kind of where it has to start, are these conversations about how we can do this together.
I also had a question in terms of like, I guess a good word for it is like confidence. Like, I think sometimes when I speak to some of like my peers, like say if they're like a white like male, you know, like when they speak, like not so much like listening to them as if like they could be just as wrong or just as right as I can. Sometimes I'm so quick to just accept what they're saying, especially we're working in like a group. You know, but also like being a Hispanic woman, I was sometimes the only Hispanic or like woman in like a room, and sometimes I struggle with people wanting to work with me. But also like my dad, you know, like sometimes he's still like he doesn't even know like what I major in. Sometimes I remind him. So it's like also thinking of like, you know, like where you found your support, people who you ask like questions to help you.
Yeah, this is great. So I really appreciate you asking about this and sharing so much that you did share. I am first gen also. And so there were many times in my journey that my parents and family members would be like, so you just want to be a student the rest of your life? Like, what are you doing? Why don't you get a job? And I was like, no, this is a job. Like, I'm doing it, you know? And then they all came to my graduation, like, we're so proud of you. Look at what you've done. I'm like, oh, we're not saying that 2 weeks ago. So it is a hard conversation to have about what we do, because it's such a black box, right? Like, still my mom's like, do you have to work today? And I'm like, I have to work every day. But are you teaching? No. But I don't understand. I'm like, oh, it's too much. It's too much to explain. Everything is a meeting. I just tell her everything is a meeting. But yeah, I think there's a real issue with isolation, especially for women and especially for people of color and women of color, for any minoritized group, really. And yeah, it can be very hard, especially in mathematics. I have tried to also surround myself with people who are maybe not just in math, but in other areas, but that are people I can be myself with and I can be fully there and they support me. We speak life to each other, I think is also important. I know some of us often make jokes about the confidence of our mediocre counterparts and how much we wish we had that confidence. And it is hard. I often think one way to combat this is to ask people to explain. So if someone gives an answer, then I'll say, oh, that's really interesting. Can you explain how you got that? And then we can work together through the explanation and pick it apart and see, is it the right route to go or is it maybe incorrect? I think that part's important, right? You can't, much like I said, this is true. Maybe you're like, she needs to prove that to me. And that's how we have to do. I mean, we're mathematicians. That's, one of the first classes we take is proofwriting. And so we don't get to just take everything for granted or for gold just because someone said it. I think we all have to prove what we're sort of saying when it comes to mathematics. That's hard though. I mean, it can sometimes feel confrontational, but I think then And I'm going to say this without even knowing if this is going to be helpful, and I apologize if it's not. But I think then you want to put yourself in a space where you can say that. And it's easier said than done. I know that. I've totally been in lots of spaces that you're describing. But once you are in a space where you can ask questions and use your voice, you will grow and others will grow. And maybe that's a conversation you have in your group right away. Hey, listen, this is the way we're going to have to communicate with each other. And if we aren't able to communicate like that, I don't think we should work together. And some people don't want to communicate like that, but then they just aren't going to be working with you. And that's okay.
I feel like you're also describing a model for great teaching,
Oh,
you know? And it's so hard to do, but but so important.
yeah. I have lots of thoughts on teaching, but we only have 2 minutes. So I will not open that Pandora's box at all. But yeah. I mean, I have more time if you want to email me, but I probably should go to the 5:30 thing that I have.
Well, thank you so much for coming for the wonderful talk and the wonderful
Thank you.
wonderful
Thank you
discussion.
so much. Yeah.
Very much appreciated. And
Thank you.
thank you so much.
Yeah, I apologize. I didn't say that. Thank you so much for this invitation. I know it was a lot of back and forth. Amanda reached out to me, I think maybe last year, and was like, "Can you come to Science Rock?" I'm like, "Yeah." And then we're like, "We're all going to be home. You want to do this virtually?" And I was like, "Yeah." So I really appreciate you taking the time for visiting, talking, all of that. Please reach out, email, check out the website if you have any other questions. This was great. So thank you.
Wonderful. And I hope we can get our students interacting more too. Thank you so much.
Yeah, you're welcome. All right. Bye, everyone.
Thank you.
Take care, everybody.
Friday.
Take care. Be safe.
Thank you. Thank you.